Okay, we'll talk today about community ecology, community ecology proper. But we'll finish with a discussion of predator-prey dynamics, one of these interspecific dynamics that we didn't get to last time. We'll get into the question of what is a community in looking at community structure, and we'll think more and more functionally as we go, as we approach community metabolism and ecosystem process. We'll focus a bit on diversity, indices for or a particular index of diversity in a community. What do we mean when we say a community is or is not diverse? We'll look at a couple of key roles that organisms might play in a community in the form of keystone species and ecosystem engineers. And then we'll spend time talking about community succession, a very nice part of community ecology that has a long history of study. We'll look at community succession. One of the classic studies in predator-prey dynamics is a study based on Isle Royale in Lake Superior, a pretty big island right here in Lake Superior, that until the early 20th century didn't have moose on it. The moose came over at some point early in the 20th century to Isle Royale and found a very suitable habitat for them. The moose are herbivores, of course, and they love swampy circumstances. They like the shallow lakes where they can wade with their long legs and eat vegetation. And they did quite well there, cycling in the population numbers, much like the sheep on Herta Island, if you read about those, in the absence of major predators. These moose did on Isle Royale. But in the 1940s, the lake froze solid and created a land bridge to the island that wolves used to cross and to arrive on the island. And the wolves found the place to their liking with all these moose to focus on. The wolves were eating other things. They were eating smaller mammals, but the moose were the focus of their diet. And so what you set up here is a neat opportunity to study population dynamics of two populations that are in close interaction in a somewhat controlled environment. Islands are wonderful laboratories for study, both evolutionarily and ecologically, because they're more controlled. The boundaries are more clear and they're more isolated from other dynamics. And holding those other dynamics constant is often a challenge in ecology. So since the late 50s, ecologists have been watching these populations closely. And what they saw early on was that moose numbers rose, followed by a sharp increase in wolf numbers, which seemed to correlate with the time that the moose populations crashed, when the wolves were at their peak in numbers. And then the moose steadily gained as wolf numbers remained low until the moose sharply crashed again, apparently in relation primarily to abiotic factors, a couple of harsh seasons. So a dynamic like this allows you to study population regulation, the various controls on populations, whether density dependent or independent, whether biotic or abiotic. And these studies are actively ongoing today, and they'll no doubt continue long into the future. And the more data we get, the more we understand these systems and can generalize to other systems. An equally famous case involves these beautiful cats. That's a lynx. It's very closely related to the bobcat that lives here in Berkeley with their little tails. The lynx has longer legs. It's a taller cat, has the very pointy ears. Bobcats have pointy ears as well. Lynx have these giant snowshoe feet because they do so well in snowy areas, and they can move around on snowy surfaces without falling in. They hunt effectively in the winter in these snowy habitats, often nocturnally. And they like to eat bunnies, specifically snowshoe hares, Lepus americanus. This is a hare that changes its pelage across the seasons to better camouflage itself in its environment, brownish in the summers, white in the winters. It's a major prey animal, as most bunnies are major prey animals. And the lynx love them, as do the foxes and the raptors, lots of things like a bunny. And you get these spectacular chases. Ooh, the drama, huh? You get these spectacular chases of lynx and hare across the snowy landscape. and the lynx survive much of the winter by eating the hares. Now, these dynamics have also been well studied. From a surprising source came the original data from back in the 1800s, long before ecologists were equipped on such scales to monitor populations like this. So where did these data come from? They came from hunters, from trappers, and the records that the governmental agencies kept on how many pelts were arrived in their offices from the hunters, who had to, by permit, who had permits to hunt and then had to register the amount of material they caught. So by keeping the books well, the Canadian government had these data to show the relative numbers of these animals through time, based on the good hunting records. Of course, many animals were killed that weren't recorded, but apparently a large enough of them were recorded to well sample the population. And what you saw over time were cycles in the snowshoe hares, up and down, that seemed to be basically followed by the cycles in lynx numbers. So these two populations are entrained somehow in numbers through time. And it's reasonable to suspect that given the short lag between the lynx peaks and the hare peaks and the bottoming out of the lynx and the hare, that the lynx are mapping onto the hares somehow in their own numbers. Well, then what controls the hare? The numbers of the hares. And that's where you open it up again ecologically to the whole scope of possibilities. And it becomes a great source of data and investigation as to what controls hare numbers. Is it biotic or abiotic? And so forth. And there have been different hypotheses for what does control hare numbers. And a few of the major ones are their food, how much food they have, particularly in the winter, in the difficult season. Predation, not just predation by lynx, but by other animals. Maybe predators cue in on them and drive their cycles. Or an unlikely source that's been suggested is the sun itself and its solar cycles, particularly related to sunspot activity, which tends to cycle on about 10-year, 11-year cycles, which is the same period of these cycles, about 10 or 11 years. And ecologists have done manipulative experiments to try to tease apart the different hypotheses and strengthen some, weaken others to see which one is the most appropriate for explaining the available data. And it's not entirely clear. There's evidence for a mix in the role of the different factors, that includes predators and food, but with a central role for the sunspots. They've excluded predators from some areas and found that the hares still undergo their cycles. They've provisioned the hares in some areas, provided extra food, so they're not starving in the winters, and they find that they do still cycle. the link to the sunspots is somewhat surprising, or at least not intuitive, unless you know something about the whole system. Because when the sunspot activity is low, it relates to how much ozone is produced in the upper atmosphere. When sunspot activity is low, there's more ozone produced. There's less ozone, produced in the upper atmosphere, because the sunspots drive the production of ozone. We'll learn more about ozone in future lectures. When there's not much ozone, more UV radiation is penetrating to the ground surface, and plants are dedicating their resources to chemical defenses against UV bombardment. When they dedicate their resources against UV bombardment, they have fewer resources to put into herbivore defense. So when there's not much ozone and there's a lot of UV, and the plants are putting their defenses into UV protection, they become more nutritious, more palatable, better food for the rabbits. And that can link to the lynxes and help to explain how the system's driven. It's fantastic. And studies are ongoing in more and more sophisticated ways involving manipulations. So we're entering the realm of community structure. And the factors we've looked at help to explain community structure. One thing I mean by community structure is differentiation among species in ecology. The type of differentiation that's visible when you go look at a community in a particular spot somewhere on Earth. Now, I study vertebrates, and much of what I'm saying relates to vertebrates. The whole field is very controversial and full of debate. Sometimes what's true and appropriate for one group, like vertebrates, or in one area, like the Caribbean in this example, isn't true at all for other groups in other places. So we always need to be careful about that. Our generalities work oftentimes, but not across the whole of life and the whole of the planet. Ecology is full of contradictions to general rules, as is biology in general. But a community like this, and we're speaking of this community of lizards, this community of anoles. Anolis is the genus of lizard. It's not a community by our typical definitions. We'll define it more clearly in a minute, community. But it's what the investigators can actually study, this group of lizards. They can't study the true community, the whole community that involves the microorganisms and the plants and all the other creatures all together, because it's just beyond their capacities, beyond their expertise and their scope and their time and their resources. So we speak of this lizard community informally, this group of lizards of different species, all in this case belonging to a single genus. And what's visible, if you go look at a system like this, is that the different species tend to be in different spots, spatially, in the habitat. Some are up in the canopy of the tree, some are along the trunks or out on the branches, some forage on the ground, some run along these fences, although I presume they didn't evolve with fences. They had some type of structure in their environment that was relevant to them. And they may be anatomically accommodating those different habits in that habitat in terms of the morphological adaptations that they exhibit. So you can often see in such systems ecomorphological connections between organism and spatial habitat. The morphology fits the function of the creature in its space. And these guys all basically eat arthropods. They all are basically eating insects, but they're dividing up the habitat by space, in space. Some organisms divide habitats in time. One of the birds that I'm familiar with in Africa, in one of these systems, I'm interested in fish-eating birds. And there's a big eagle there, much like our bald eagle, but more of a dedicated fish hunter on the open waters. And when it goes to sleep, the big owl comes out that also eats fish in that habitat. So you get an eagle by day and an owl by night, both focusing on big fish at the water surface that they can catch with their talons. And they don't like each other at all. If they catch each other at dusk or at dawn, the eagle tends to pick on the owl. They don't get along. They differentiate the habitat temporally as opposed to spatially. So this sort of spatial differentiation and structure is a part of this community. They're partitioning the resources based on space here in this case. And how did this come to be? Did these lizards all evolve on different islands? This is the Caribbean, Dominican Republic, I believe, from this example. Did they all evolve on different islands and then come to be assembled on this island in this place, having acquired adaptations to these different types of habit? Or did they evolve in situ on this island and differentiate into these different roles on the basis of something like competition? It's an open area for investigation. If someone who argues that competition led to the structuring of these communities in situ might be challenged on the basis of someone coming and saying, look, I don't see them competing. They're all just doing their thing. Recordia is up here in the canopy, and the Sticus is here on the fence, and they just don't interact. They don't compete. One's here, one's there. Well, then your first investigator who thinks there is a strong role for competition says, well, they must have competed at some point in the past. And what you see now is the result, this differentiation. Somewhat disparagingly, the second investigator might say, you're referring to some ghost of competition past that helps to explain what you see today, but show me the actual competitive interactions. So that debate would continue from there. But the ghost of competition past is available here as an explanation for what structured this community evolutionarily. Competition has been a main source of study, as I've mentioned, and also in this community context. One of the better spots to find evidence for competitive interactions is in the context of character displacement. And a nice example comes from the Galapagos, with finches in the Galapagos. Fuliginosa and Fortis are two finches, two of these ground finches that have different sized bills. You can measure their bill top to bottom as a simple metric of its size, and that relates to its capacity to eat hard objects. The heavier the bill, the better equipped it is to eat hard things like hard seeds or larger seeds. You have a neat natural experiment in the Galapagos because these two species live allopatrically on two islands. They don't coexist on Los Hermanos and Daphne. They live by themselves. Fuliginosa occupies Hermanos, Fortis occupies Daphne without the other species. And in those situations, they have relatively similarly sized bills. The depth of the beak is about the same in terms of percentages of individuals in each size class on this histogram. Beak sizes are about the same on those two islands for the two different species when they live by themselves. But on the islands where they live sympatrically, where they coexist, you can see that Fortis shows a much bigger beak than Fuliginosa, both of them differing from the averages typical of their populations when they exist in isolation from the other species. That is suggestive to many people of a competitive interaction that leads to differentiation, morphological differentiation, related to resource use. Hard and heavy and large objects, feeding in the case of the one, smaller objects which can be more finely gathered in the other. Because a really big bill is actually awkward to gather small, fine objects, which a small bill is good at. And those large objects may be completely out of the range of opportunity for the smaller bill type. Suggestive of competition for many people, these examples of character displacement. And there are other good examples. So what do we mean by a community? You get pictures like this in textbooks to illustrate a community. That's a very lush tropical environment with a bunch of different species all living in close proximity, interacting at some level, presumably. Here's another one, a community. You've got the trees, you've got the deer that's been photoshopped into the front. You have microorganisms in the soils, for sure. You have fungi growing all around and birds flitting about. It's meant to encompass the whole system. All the different species in the system is the community. A group of populations of different species living close enough to interact. Something simple like that, if you want a definition. How the boundaries around the community are set, or where are the boundaries of these communities, is a part of the problem in defining a community. The boundaries often aren't that clear. And they're best set by the investigator based on the questions they're asking. You become practical. Well, the community I'm interested in studying is bounded this way because those are the boundaries of the park. And everything else is urban environment. So my natural boundaries are this park. Or I'm working here and another investigator's working over there, and we actually don't get along that well. We compete professionally. So I stay here and she stays there, and thus the community I'm studying is this one, and these are the boundaries. That's driven by practical necessities about your academic standing or something. You draw the boundaries as appropriate. And ideally they're set by the organisms and their patterns, rather than your professional difficulties with your colleague or something like that. Sometimes the boundaries between communities are quite clear because of abiotic differences in the environment that influence the organisms. Here's a nice photo from near the Stanford campus of plants, many of which are flowering plants, small herbaceous flowers in the foreground, and just more of the grasses in the background. And the difference is driven by the bedrock, the rock underneath this, that influences the soil on which these plants grow. Serpentine rock here in the foreground underlies this vegetation and contributes a lot of magnesium to the soil. And that favors the growth of some of these flowering plant species, whereas the sandstone rock in the background creates a more nutrient-poor soil system that influences and that doesn't allow as many of the flowering herbs to grow and creates more of a grassy condition. So you have this nice boundary that maps onto the geological difference below the soil. There your boundary is neatly laid out for you. Or major boundaries like this. You have an aquatic system flowing through here, meandering back and forth, and no doubt it spills over in some years. So you often have a floodplain like this that's periodically flooded. Maybe there's standing water even in here. Maybe it's marshy. Well, trees can't grow in an environment like that, most trees. And so the boundary of the trees is related to the waterlogging of the soils, probably. And so you have a nice forest edge created here, a very distinct edge, where you move from one system to the other and you add a clear boundary based on the abiotic differences in the two systems. And there's a lake back here, and that's an aquatic ecosystem. A different biome, if you want. Not really the appropriate scale classically to think of a biome, but yeah, it's a completely different system. It doesn't have trees growing in it, the lake. No, it's a lake. And this is an open grassland, and that's a flowing aquatic system. These are all different systems, and the boundaries are pretty clear in those examples. But if you wanted to study a patch of this forest, well, where's your community? This might be a little rise in elevation. There may be a little watershed here you can identify where the water pools through. Okay, that's going to be those are my boundaries, because I'm interested in the birds and the squirrels in this system, and that's all I can handle. I'm just one PhD student with a couple of assistants each summer. That's what I can handle. So I'll bite off that piece and call it a community. And really, I'm just focusing on a few vertebrates and their food, but I'll call it a community. It doesn't have to include absolutely everything. Nobody can study absolutely everything all at once. One of the major properties of communities is their diversity, which reflects the number of species in the community and how relatively abundant the species are. Which of these communities, represented by these different species with their different shapes, which of these communities is more diverse? You have an inclination, I think, to say that this is more diverse than this, even though both have 3 species. Each has the star species and the triangle species and the circle species. Sorry, I wasn't very creative when I was making this yesterday. But those are your 3 species. This one also has only 3 species, the same number of species in each community. But there are more of those rare species in this community than in this one. They're more evenly distributed. They're more even in their abundance, the relative abundance of them in terms of individuals within the species. And intuitively, we know that's part of diversity. So we distinguish terminologically those two things by speaking of richness, species richness, and species evenness. So these two communities are equally rich. They have 3 species. Species richness can be just used in this context to count the number of species. 3. They're equal in richness, but they have different evenness. And both go into our measures of diversity, both richness and evenness. There are various indices available to quantify diversity. And if you go into upper-level biology classes, you'll often get into studies using diversity indices. Almost every year I teach a course that runs field projects, and almost every year I get a paper on diversity of some creature in the area that's really just looking at species richness. They're not actually looking at diversity, because it's hard to count the numbers of individuals. But you must if you want to talk properly about diversity. So one of the available indices is an index like this one, the Shannon Diversity Index. And I'll run you through it real quick, and I'd like you to march through it on your own time with a calculator. I also added the results here again yesterday. I think I plugged them into my calculator correctly, but I just want to show you how easy it is so that you can do it. Again, if you do this yourself on your own machine, you'll just get a better sense of what I'm talking about here. All you do is take your different species, 4 in this case, and determine how many there are, the percentage that exists, the proportion of each that exists in the community. And then you use this equation to generate your index, your Shannon Diversity Index, where your proportion of A is multiplied by the natural log of the proportion of A, and you add that sequentially to each species in the community. And when you do that, what you get is plugging numbers in like this, 0.25 to represent your 25%. Make sure you keep your little negative sign out there, and you march it through, and you crunch the numbers. It's not too hard, and you get your index for that community. You do it for your next one. Check my math. And